Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, and you know what? It's been a minute with me as well, at least for new videos. If you watch some of my old videos, then I guess I'm always there, but I haven't recorded a video in a couple months. I really haven't needed to. You know, that's the luxury of having these videos for my students. I can replay them and have any other resources for them at their disposal at any time. Plus, I've been a busy boy. I coach softball during this time, and I do a lot of tutoring on the side as well. And I just haven't had to record anything, haven't needed to. Well, tonight I do, and for my Integrated Math 1 class, we are doing a cumulative review of everything we've been doing this semester with certain skills, and I'm going to look at all those skills. They're by numbers 16 to 25. Those numbers won't matter to you so much, but 10 different skills where we jump into some geometry in a bit here. And let me run the gamut of the different problems we have here. So these are all different handouts that they have. I'll do a PDF of the entire thing, making a large handout here, and we'll count how many questions there are too. But skills 16 to 17, there are 8 questions on the front, 8 on the back. You got some word let me say what they are. Skills 16, geometric sequences. Determine if something's geometric or not. Write the geometric sequence, find the number of terms, write the rule. And then word problems, all basically of the same variety. You're going to need a calculator for these ones here. Then we move on to skills 18 and 19. Skill 18, graphing exponential functions. You can see these 4 right here. That's all I'm going to do. Skill 19, solving exponential equations by rewriting the base, matching your bases right there. Skill number 20, this is where we start to hit some of the geometry stuff. Find distance and midpoint between each pair of points. Each problem here, all of 1 through 8. The first 4 have graphs, the last 4 do not. And then you have segments, segment addition postulate, where 2 lengths add to a whole length like that. Sometimes they're drawn, sometimes they're not. Midpoints here on a segment where you can still solve for x, find missing lengths. Angles, the same way that segments are. You have adjacent angles where 2 measures can add up to the entire measure like that right there. And angle bisectors where it divides the thing into 2 congruent parts, set them equal and go. This back half is slope, parallel and perpendicular lines, finding out whether slopes are parallel and perpendicular, and writing equations of parallel and perpendicular lines through these equations right there. And then the last 2 are kind of one the same. They have to do with angle relationships. Vertical angles, linear pairs, corresponding angles, alternate interior, exterior angles, same side interior, exterior angles. Hopefully you've heard some of these things before, and even though, listen, I have some videos of old with these, just not in sequence for recent. Oh, there's a front and back of this as well. Just not of recent, right? So you're going to have to find some old ones here. I think in total, when I just looked at those, 16 plus those 12 is 28, plus another 16 is 34. No, 44 plus 16 is 60 plus 14. 74 problems. 74 problems, and I've already rambled for a couple minutes here. I want to try and average a problem a minute a problem, whatever way you want to say that there. Now, I did a review video like this last semester, and there were just under 100 problems, and I still got under an hour and a half, so less than a minute a problem on average. So I'll definitely speed up within a skill as I go. That's basically me doing the problems now here, right? We can't run on forever with this. We could, but I'm going to choose not to tonight. So I'm a little rusty in maybe making videos. You're going to have to be okay with me on that. I'll just talk about the kind of problem that we have and what we're doing as a rundown. All right, skill number 16, geometric sequences. That means a list of numbers like this one. Well, if it's a sequence, this one is. But a list of numbers that are separated by a common ratio. You're multiplying by some r, some value, the same value over and over to go from one number to the next in this list of numbers. Is this the same r right here? I'm going to do a test. Does 2 times what is negative 6? I'm sure you know it's negative 3, but you can test it by doing negative 6 divided by 2. Let's see if 18 divided by negative 6 gets you the same thing, because that means you're multiplying by the same thing, and negative 54 over 18. Yeah, all of these reduce to negative 3. Common ratio is negative 3, so yes, this is a geometric sequence right there. If it is, find the common ratio, what they said here. These next ones, we'll check these out. 103 times what is 1032? I don't even know that, but we'll do a test. 1032 divided by 103. We'll also test to see, is it the same as 10,322, excuse me, over 1032? And is it also equal to 103,222? Basically, they're just adding 2's at the end. I don't see any reason why this is going to be a common ratio, if you could tell me what it multiplies by. But let's just check this in the calculator and see what's going on. The numbers are probably close. Arguably, it's probably somewhere close to 10. Right? So 1,000 32 divided by 103. Now, it has to be exact. See 10.019, da, da, da. Now, let's do 10322, and only if it's exact can we accept. It's very close to each other, but not exact. There's no common ratio. It's multiplying by something different, very slightly something different. And the last one here, that piece de resistance, to show you, once again, multiplying by something slightly less than 10 each time, or not less than 10, but slightly less than the previous one, but more than 10 each time here. Not a common ratio, which means not a geometric sequence here. I show that these are not the same just by saying, no, these are not the same here. No, not a geometric sequence. All right, and that's a good test you can do. Okay, number 3 and 4, find the next 3 terms in each geometric sequence. So again, determine what you're multiplying by here. This time I tell you it's geometric, and all the rest of these are geometric. So it's like we're not checking to see if they are. They are. So if I figure out what negative 2 times what is 12, then it's going to be the same thing here automatically. I don't even have to check. And that's going to be negative 6, right? I'm multiplying by negative 6 each time, which means to find my next 3 terms, and this is going to be the, this is the first term, second term, third term, fourth term. I'm going to call it a sub 5 to find the value of the fifth term. That's 432 times negative 6, and that gets me my next value. So let me just calculate right now. I did 422. 432 times negative 6. And the sign's going to change, negative 2,592. Now, to find the sixth term, I'm going to take negative 2,592 and multiply that by negative 6. So just times negative 6 each time here. You don't have to show all this work. Well, you can, but not a requirement of any sort of way there. But just to kind of give you the idea of what's going on. And what I'm doing is called recursion. I am iterating the same rule, the same idea from the previous term to get the next term. In other words, if I wanted to find the 20th term, I'd have to first get the 19th term to do it, unless I come up with a certain rule for this, which we'll be able to do in some future problems here. So these are the next 3 terms of the geometric sequence right there. 5th term, 6th term, 7th term. I was using my calculator to multiply those, by the way. All right, number 4. Now, these numbers are dwindling down. Now, you can think of this in one of 2 ways when it comes to you computing. But when it comes to doing a sequence, I want you to understand that we are always asking what we're multiplying by, not what we're dividing by. That being said, we are dividing by 5 right here. This is divided by 5 and divided by 5. You notice all the values are negative. The sign stays the same. That means we're dividing by a positive number, and it's keeping it negative. We are dividing by 5, but what are we multiplying by? Because if I ever had to make a rule, that's what I want to know about. And the answer is 1/5. You're multiplying by the reciprocal right there, times 1/5 times 1/5. If you're not sure, what can you do? Divide a number by the one before it. Negative 500 over negative 2,500. Your calculator will probably say 0.2. But if you know how to reduce this, they can both divide by 500 and change signs. That becomes 1/5. So you are multiplying by 1/5, which is the same as dividing by 5. All I'm trying to find are the next 3 terms. However, I want to make sure you're aware of that. So what are the next 3 terms? Next 3 terms, negative 500 divided by 5 is negative 100. Negative 100 divided by 5 is negative 20. Negative 20 divided by 5 is negative 4. And the sign doesn't change. Those are the next 3 terms right there. Same thing as times 1/5. Keep that in mind. And keep that in mind for when we have problems like these. And when we have problems like our exponential graphs on scale 18. Keep all those in mind when we do it. Okay, find the first 4 terms of each geometric sequence and the value of the term requested. Now, this is known as an explicit rule for a geometric sequence. If you previously heard me say that if I wanted to find the 20th term, I'd have to know the 19th term, right? Because then I have to apply the rule. That's true if I use recursion. An explicit rule is really cool. I can find any term that I want just by plugging my number into here. And the overall rule is a sub n equals a sub 1 times r to the n minus 1 power. Might look like foreign language to you if you haven't seen this before. A sub 1 means take the value of the first term, in this case it would be 3, and multiply by your common ratio, in this case negative 3, and minus 1 times to get the nth term. So we start from the first term. If I want to find the 20th term, I'm going to multiply by my common ratio 19 times. From the first term, second term, third term, fourth term, that's how many times I multiply by it. So 19 times to get to the 20th term. I want to find the 9th, before that, I want to find the first 4 terms. Okay, let's use recursion for that. Your first term is 3. Your common ratio is negative 3. So your first 4 terms are 3, negative 9, 27, and negative 81. If I'd like to find the 9th term, I could keep multiplying by negative 3 over and over. But let's go ahead and use the rule this time a sub 9, you take 3 and multiply it by negative 3 to the 9 minus 1 power. That's the 8th power. And this is where you get to use your calculator. This is where I get to literally type in what I just did right there. So I can do 3, parenthesis, negative 3, close parenthesis, raised to the, where I've been using another calculator so long, raised to the 8th power right here. It's going to be a positive number there. 19683. Got to use parentheses around that guy right there. So 19,683. That is the... it grows fast, right? It goes big fast. We saw this on these other ones. It grows big pretty fast there, so just be ready. All right, number 6 right here, write out the first 4 terms. Negative 1,024 is the first term. So there's the first term. And then 1/2 is the common ratio, with taking half of values divided by 2. So divide that by 2. I should know these. Negative 512, negative 256, and negative 128. Those are the first 4 terms of the sequence just by dividing by 2, or in other words, multiplying by 1/2. A sub 11 is the value of the 11th term in the sequence. I'm going to substitute 11 into the explicit rule. I believe that's the faster approach than going many terms more to do that. And I'm going to let the calculator assist me. Actually, I know 1/2 to the 10th power. I know 2 to the 10th power is 1,024. Oh, that number is 1,024. So it'll be negative 1,024 times 1 over 1,024, which is negative 1. I should just know that one there. You can use the calculator, give it a shot. Make sure you put parentheses around the 1/2. All right. First 6 down. Let's go to number 7. Write the explicit rule. Oh, and 8. Then find the value of the term requested in the problem. So it's going to be a lot like the previous one, with the difference being this time we don't have the rule itself. And if we use the rule, then we can find the value of the term as well. So right here, we're multiplying by negative 2, and the first value is a positive 2. So first value is positive 2, multiplying by negative 2. Let's write that a sub n equals a sub 1 times r to the n minus 1 power. That is known as the explicit rule. And I'm going to use the explicit rule to then find the 10th term. 2 times negative 2 to the 10 minus 1 power is to the 9th power there. If I was right, that should actually be negative 1,024, because that's 2 times negative 512. So I'm just going to go off the math that I know from that. Use a calculator. Number 8, we're multiplying by 3 each time. Now remember, if it was going down, we'd be multiplying, say, by 1/3, not, say, divided by 3. We'd be multiplying by 1/3. So your first term is 1. Your common ratio is 3. So your rule, a sub n equals a sub 1 times r to the n minus 1 power. You know, you don't actually even need the 1 there. I could write it like this, and that would be perfectly accepted. It just doesn't really spell out that your first term's a 1, though, right? So we might want to write it like that for our own sake. But for computation purposes, it doesn't really do anything. So the 12th term, again, 1 times whatever is just that whatever, and 3 to the 11th power, 12 minus 1 happens. I don't know 3 to the 11th power, so I'm going to go ahead and compute that right now. But 3 to the 11th power will give me my answer. 177,147. 177,147. There we go. 177,147. 12th term of that sequence. And that is my quick set of geometric sequences. That is skill number 16. 13 minutes in, moving forward, we're going to be writing a model for exponential growth decay functions and find requested values. Now, the overall equation that I'm going to be using looks like this. Okay, it says y equals a times 1 plus or minus r raised to the t power. Now, a represents whatever initial value we're talking about when we are at time 0, whether it's year 0, week 0, month 0, second 0, whatever it is, hour 0. We are going to add or subtract some r. This is our rate, I should say, our percentage value that we have to convert to a decimal. We're going to add or subtract it from 1 based on whether it's a growth or a decay. 1 represents 100%, because remember, we convert it into decimal form. We make it 100 times smaller, because that's how you compute percentages. If I want to take 50% or something, I multiply it not by 50, but by 0.5, where that decimal moves 2 places to the left to go from 50 to 0.5. Anyway, if I want to do a percentage increase of something, it's got to be 100% of what I have plus that amount. And a percentage decrease or something, I take 100% what I have and take away that amount. So when I'm asked to write a model for these things, the model is represented still with t years or t time, whatever it is, before the question that's asked about, for example, number 9, 18 months from now. on the 7th bounce on number 10, 13 years from now on here, that t will be substituted later. So I'm going to start with a model, simplifying the inside, adding or subtracting the r for each problem. And then I'm going to compute the value and go with it. And I'm going to use the calculator to help me. I'm going to often round to, if it's money, I'm going to round to 2 decimal places. If it's a population thing, I'm going to round to 0 decimal places because we're people, not decimals of people. And if it's just something else, I'll probably round to the nearest 10th or 100th, whatever you feel most comfortable with for the time, just for precision. But always write units for your answers. All right, number 9. A company promises to release a new smartphone model every month. Each model's battery life will be 5% longer. That's going to be about R. And longer is an increase. R is going to be 0.05. That's your 5% as a decimal. Then the previous models. If the current model's battery life is 665 minutes, that's our A value. What will the latest model's battery life be 18 months from now? What's the Y value, the final amount after T 18 months? So that's kind of how it works here. But I'm going to start with the model portion. Y equals, I'll take 665, and I'm going to do 1 plus 0.05 raised to the t power. Again, model kind of still has that t because this is for any number of months t. And 1 plus 0.5 is 1.05. So this is the model portion of this, if I were to write that out. That's not the answer, but this is the model that I can use to, I can graph that, I can have a curve, and I can predict any t for that. They want 18 months, let's give them 18 months. So let's do 665 times 1.05 to the 18th power there, if t is a number of months. And this is where the magic works in the calculator. The rest of it, I only need the calculator for. I'm going to go and do that right now. 665 times 1.05 raised to the 18th power. Remember, your calculator knows order of operations. So enter about 1600 minutes. I'll round to a decimal place, 1600.4. So 18 months from now, that's a lot of models every month. I hope this company's thriving. So this is about 1600.4 minutes. And I would have done 1600 because it sounds so clean. But because this problem had a little 0.0 on it, I figured, let's put the 0.4 on that. Now minutes, right? That's the new battery life of that phone 18 months from now. Far improved. That's a big improvement. It was 665 before, which is about 11 hours. 1600 is about, don't make me do math, probably just under 17 hours. No, I'm sorry, not 17, 27. I think just under 27 hours. I can't math that right. That's a lot of hours, I guess, compared to what it was a year and a half later. All right, number 10. A rubber bouncy ball is dropped from a height of 102 inches onto a hard, flat floor. After each bounce, the ball returns to a height that is 16.8% less than the previous maximum height. What is the maximum height reached after the 7th bounce? So the ball starts up here, it bounces, hits up here, hits a new height, bounces, hits up here, a new height. That's 16.8% less than the previous one. What happens after 7 bounces? Now, 102 inches is my initial. That's my time 0. It's my bounce number 0. It hasn't bounced yet. There are no heights yet recorded after any bounces. I'm going to record the height after the 7th bounce if it keeps this rebound ratio over and over right here, that percentage. And that's 16.8% less than the previous, not 16.8% of. Right? So I'm going to subtract that from my 100%. So my model will be y equals 102 times 1 minus, now 0.168. So 2 things are happening here. Number 1, I'm subtracting instead of adding because it's a decrease in percentage. Number 2, again, converting the percentage to decimal form. This has a decimal. That doesn't mean it's decimal form. The 0.168, 2 places over, 16.8 divided by 100 gets me 2 decimal places over. And if I simplify that inside, which I always ask my students to do, some just don't pay attention to that, and some hopefully they're catching on. That's 0.832 if I believe my math serves correctly there, and that is my model for this thing. Now I can find out after t bounces, what is the height of my ball in inches after t bounces? Yes. Okay, so right here I'm going to go ahead and substitute now after 7 bounces. Model first, this second. That's a 2 right there. 0.832 to the 7th power. If I did that calculation correctly, let's try that. 102. I'm not going to show you my calculation. I'm just going to work fast. 0.832 to the 7th power. Looking at about 28.15 inches. I'm just going to put that 28.15 inches. I want some precision on that guy right there. Inches are my units. Okay? All right, number 11. A savings account balance is compounded annually. All that means is at the end of the year, that's when they start to add the stuff in. Don't worry about that too much. If the interest rate is 4% per year and the current balance is $1,755, what will be the balance 13 years from now? What will the balance be? So initial amount in my model here, $1,755. Interest rate is an increase for us. Think of interest as increase. 1 plus 0.04 to the t power. That is 1,755 times 1.04 to the t power. That's my model. And when I calculate this, I'm going to make sure to round to 2 decimal places because it's money. I want my cents on the dollar. So 13 years from now, let's do 1,755 times 1.04 to the 13th power. That is going to be... Sorry, got to calculate things to the 13th. $2,922.20 if I, round that way. $2922.20. Okay. Number 12, an architect is designing a tapered office tower where the ground floor, ground zero, is the largest. That works our time t. It's not really time this time, but it's instances of floors. Unless they're building it. They're designing the office. The ground floor is the largest and the floor space is reduced by 7% per floor. Think of like the Transamerica building or something like that. It gets smaller as it goes up, I guess. Or just in terms of floor space. If the ground floor has an area of 1,390 square meters, what is the area of the 20th floor? Now you don't square 1,390. Those are the units those are two-dimensional units right there. We're in meters here. So y equals, so the initial amount or the ground floor, T0, is 1,390. We are going to be taking away 7%. Now, we're going to be doing 1 minus 0.07, which is 0.93. I'm going to start writing that here on out so I just get my model. Okay. Now we're going to go ahead and substitute 20 in for T right here. So 20th floor. Understand, substituting 20 in there. So we're going to do 1,390. This is kind of where I get to do a little bit of speed up if I'm able to. And you're going to ask, how did I compute that? I substituted 20 for T. And I'm getting, whoops, I just substituted 2 for T. That would be the second floor. 20 for T, 325.6. 325 about 0.6 square meters of floor space right there. Number 13. An employee receives a 2.9% raise once per year. If the employee's initial salary is this much, what will the employee's salary be after 6 years? So once again, as a model, 2.9% raise, that's 0.029. We're going to add that to 1. 1 plus 0.029 is 1.029. 67,500 times 1.029 raised to the t power is the model. So 6 years later, we're going to substitute 6 into there. So 67500 times 1.029 to the 6th power. And I'm getting $80,130.16. Don't believe me, try it for yourself. $80,130.16 right there. Never leaving out my units. Never leaving out my units. For tax purposes, a car rental company assumes each car in their fleet depreciates by 10.4% per year. Their value is going down. There's an appreciation and a depreciation. 10.4%, we're going to take off of 100%. If the initial value of the car is $31,100, what will the value be when the car is 12 years old? So our model, $31,100 times 1 minus, 0. Let me try that again. 1 minus 0.104. That's going to be 0.896. 0.896 raised to the t power is my model. And then the value, 12-year-old, right here. I'm going to substitute 12 into there. 31100 times 0.896 raised to the 12th power. 8326.39, I'll round up. $8,326.39. So don't wait around. Get your car at $31,000. No, I don't know. You wait 12 years, then you save yourself a good $23,000. Hey, you know what? It's a lot. It's a lot of waiting as well. All right. Number 15. A new social media site is increasing its user base by approximately 4.3% per month. So months here and 6 months from now, if the site currently has 33,240. 33240 times, we're going to do 1 plus, not 4.3, but 0.043, right? Oh, whoops, I wanted to clean that up first. 1.043 to the t power. T is in months, so 6 months from now, 6 months, 6 meses. 33240, whoops. Sorry, you can't see what I'm typing. I just missed a 3, apparently. Times 1.043 raised to the 6 power. Now, there's a decimal. It says 42792.4218. People are not decimals. We're going to say 42,792 users. Users. Right there. All right. A robot vacuum cleans a dirty floor using multiple passes. During each pass, 21% of the dirt is removed. If the floor initially has 16 ounces of dirt, how much dirt will remain after 13 passes? So 21% removed, that's our decay. We're going to do y equals, where do we start, 16 ounces? 16 times 1 minus 0.21, which is 0.79, raised to the t power. There's our model. 13 passes. I guess that's kind of time. 13 passes later. Should be pretty small, taking away that much. 16 times 0.79 raised to the 13th power. 0.7469 da da da. Less than an ounce. I mean, I guess it makes sense. We started at 13. I'll say 0.75. 0.75 ounces of dirt. And that makes sense. It's clean up. It did 13 passes, man. This robot vacuum better clean up most of the dirt. I want to get it 100% on one pass. All right, that is skill number 17 right there. Skill number 17. I'm going to go ahead and move forward. We're going to do 4 graphs on skill number 18. Sketch the graph of each function and find its domain and range. Now, I've had videos on this before, so I'm not spending a long time on this. You want to find it, type graphing basic exponential functions. There is no horizontal or vertical shift here. This is y equals ab to the x power, where a is your y-intercept, and b represents your growth or decay factor, which means what I multiply by every time x increases by 1. I might do some tables here and there to get things started with. If my y-intercept is 5, that means there's a point on my graph that is 0, 5. And think about your geometric sequences. Just like every time there was a new term, you multiplied by your thing. I want to multiply by 2 going to here. 5 times 2, that gives me 10. There's a point that's 1, 10. When x is 2, 10 times 2 is 20. Very geometric-like, right? You can plot those if you'd like to. Here I got to divide by 2 going to the left, because I had to multiply something by 5 to get 2. And I know everyone wants to say 2.5. I'm going to say 5 halves, knowing that that's also 2.5. That divided by 2. How do you do 5 halves divided by 2? You multiply by 1/2. That's 5/4, which is 1 1/4. So you can see where there's benefit to that. And 5/8 is next. That's at -1, -2, and -3. This just becomes half of what it is in that direction. And it gets closer and closer to your asymptote there. I don't imagine I want to do a lot more tables here, and sorry if my graph gets a little weird on the squiggly sense. I'm using my stylus here. And there's my asymptote, the thing that we do not actually touch across, we just approach. This is positive exponential growth. The domain of this is all real numbers. This hits every value in existence left to right. The range is y is greater than 0. These are going to be very redundant when it comes to me answering these. Domain will always be all real numbers. We're always going to be greater than 0 or less than 0 for domain and range. All my points are positive. All right, number 2. Y equals -4 times 2 to the x power. Now this time, let me move myself over here. This time, -4 is my y-intercept. That's 0, -4. And as x increases by 1, we're multiplying another 2 to our y values. -4 times 2 is -8. -8 times 2 is -16. And I divide by 2 as I go to the left. Take half of my previous value. Half of -4 is -2. Half of that's -1. And -1/2. -1/4, -1/8, you get the drill. This is the graph. It is negative exponential growth. It takes off in the negative direction. It is considered growth. This graph should not look that bad. I can't even excuse that sloppiness. Let me try that again. A little bit better. It kind of curves off at the end, my bad. Okay. Negative exponential growth as it takes off in the negative direction, like that as x increases by 1. Domain is all real numbers. Range is y is less than 0. Now we're underneath the graph. Every value is negative. The graph kind of assists you in letting you know what's going to happen, right? The scales are clearly positive, negative. I mean, but it starts from the y-intercept. Is the y-intercept positive? It's based on A. Is A positive or negative? A is positive, so we're going to stay positive. This time, though, there's decay. I'm multiplying by 1/3, dividing by 3, if you will. But I think it's easier to say 1/3. 2 times 1/3 is 2/3. 2/3 times 1/3 is 2/9. So you can see where I'm going with that. How do you plot it? It's kind of close to 2/8, which is a quarter, and it's shrunken. Now I'm multiplying by 1/3 going to the right, which means I'm dividing by 1/3 going to the left, and 2 divided by 1/3 is the same as 2 times 3. I am tripling my values because I got to take 1/3 of 6 to get 2, and 1/3 of what gets me 6? Well, 18. So as I go to the left each time, I'm becoming 3 times larger as it becomes 3 times smaller when I go to the right. This is known as positive exponential decay. We've seen some decay from the previous word problems we were talking about where things decrease by certain amounts. So this has a domain of all real numbers. Sorry about that. And a range of y is greater than 0. You can see where I want to put an emphasis on speed a little bit more because I feel like I'm a half hour in. Number 4, -3 times 1/2 to the x power. Once again, a fraction, but this time from the negative end. Half of -3 is -3/2, -1.5. And then -3/4, right? -3/2 times 1/2, you multiply the 2's. And then -3/8 as it gets lower. And then we divide by 1/2 going to the left. -3 divided by 1/2 is times 2. That's -6. And -12. Now I've stated these ad nauseum to my students here. I'm gonna just go ahead and call out my students with this. If you're still having trouble with this, I'll be honest. Listen, you're not paying attention. You're not trying. You're not applying. You're not asking questions. I'm not really calling you guys out on it, but I'm saying it like it is. For the number of weeks that we've been working on this stuff, if you're still caught dead with confusion, you're just not paying attention. At some point, you can build a table. It takes time and whatever else. So hopefully we're getting there. Domain all real numbers. I don't really ask them about domain and range right now. Range y is less than 0. That is skill 18. 3 skills down, 7 to go. Moving on. We're going to solve each equation here. Now these problems, I'm not going to spend a long time on talking about each individual problem. The concept will be the same unless I throw in a new wrinkle in what's happening. The general goal of these is you want to try and get the bases to match. The idea is if you can get these things to have the same base, then you can set the exponents equal to each other. Right? How else can 3 to this power equal 3 to that power if these two things aren't the same? They're both 3 to a power. They have to be the same. So right now, base matches, set the exponents equal to each other, and solve. The rest is algebra. Now, I'm not going to spend time on the algebra except to state, make sure your numbers are exact, which means use fractions. I'll add 3a over, subtract 1 over, and divide by 6. I get -1/6. Not -0.16 repeating, or not -0.167, -1/6. That's it. Now, number 6 is a little different. I don't have matching base, but I also need to get this exponential term by itself before I can get a matching base equivalent. I got to subtract 8 over. 4 to the 3a equals 16. I want to see, can I raise 16 as 4 to some power? And the answer is you betcha. It's 4 to the 2nd power. So I didn't change 16. It's still this value. I just rewrote the way it appeared. So now I have a matching base, and I can compare the exponents equal to each other now. 3a equals 2, divided by 3, a equals 2/3. A lot of these answers end up being fractions. I think the general idea is to really get my students at least to really accept the fact that that's how your answer should be written in some things. Maybe that makes it a little harder or untrustworthy. All right, I got to get this term by itself, multiplied by a -3 and adding with 12. Note that I cannot multiply these together just as much as I cannot add these together. There's an x there in the exponent. PEMDAS states exponents first, then multiplication, then addition. So I got to subtract the 12 over. -3 times 4 to what power gives me -192? Let's divide that -3 and figure that out. -192 divided by -3 is 64, positive 64. So 4 to some power is 64, and you betcha it is. That is 4 to the 3rd power. That makes x equal to 3, and I'm done. I've solved. You can double check these, but it looks good. Number 8, same thing. I can't multiply these. They are multiplying, but it's 2 to the 2k power. So I'm going to divide 32 over. And let me write it this time, because 4 over 32 can reduce to, that is not an x, can reduce to 1/8. Now I got to match base, and this is a fraction. Well, 8 is 2 to the third power. I didn't match base, but I have the idea of what base I want to match, which is 2. I need to make this side say 2 to some power. Negative exponents are what get us those values in the denominator, and it's not the last time you're going to see that even on this page here. So if I want to rewrite this as 2 to some power, it's 2 to the negative third power. That's how that's working right there. Now my bases match. 2 to some power is 2 to some power, and I can set the exponents equal to each other here and divide by 2. I get negative 3 halves, which is negative 1.5, but when's the last time you saw me write that? Stick it as that, keep it as the improper fraction. All right, number 9, 8 to some power equals 2 to some power. We saw that 8 is 2 cubed, so I'm going to start working on that. Only it's still this quantity being 8 being raised to this power here. So although I have the match base idea, it's not quite a base of 2 yet. It's still 2 cubed raised to that power. Well, there's another property involved that says if you go ahead and, I got to find a marker or a thing that I haven't used. If you raise not a power to a power, but that a base with a power to a power, then the exponents end up multiplying. And that's exactly what's going to happen here. 3 is going to multiply not just with x, but x minus 1. I'm going to distribute. So I get 2 to the 3x minus 3 power equals 2 to the x plus 2 power. Now I have a true matching base. I should really check off when I match the bases because then, and they don't cancel. I don't divide by 2, nothing like that. Actually, if I'm getting rid of them, it's involving something called logarithms, something that my IM1 crowd isn't going to hear for 2 years. But the point is, it's a logical step. If those two values are the same, the only way these are equal is if these two values are the same. So what value of x gives us that? I'm going to subtract x from both sides to get 2x and add 3 to both sides to get 5 and divide both sides by 2. I get x equals 5 halves. So I don't know if the problems are easy or hard, but you do get some fractions in them. So that's just that last step to do here. 64 to some power equals 16 to some power. Now, 16 is the smaller number. Sometimes you want to think, can I do 64 as 16 squared or to the fourth? No, 16 squared is 256. So the difference with this problem is you're going to find a matching base, but you need to change both of them to match that. 64 is 2 to the 6th power. 16 is 2 to the 4th. I can do that. It's also 4 to powers, and we've seen it a couple times. 64 is 4 cubed. So I'm going to go with a larger base if I can, and 16 is 4 squared. Now you just saw in the last problem here, we do multiply these exponents, so that's 4 to the negative 9m. And I'm going to distribute this 2 into these two terms here to get negative 6m minus 2. So 4 to the negative 6m minus 2. The bases now match. I can go ahead and set these exponents equal to each other. Negative 9m is negative 6m minus 2. Let's add 9m over here to make this positive, add 2 over here, and then divide by 3. I get 2/3. I've seen the 2/3 before, but for a way different problem. All right, 2 more. Number 11. 1 over 216 to the x equals 36 once again. And, you know, for my students, they generally have what's called a power table, just an idea where you can find what power things I can work with here. 216 is 6 cubed, and 36 is 6 squared. Trying to get a matching base right there. 1 over 6 cubed is 6 to the negative 3rd power. We've kind of brought that up before. Notice the x still on the outside. Don't get rid of the x. It's the whole thing you're solving for. Negative 3 times x is negative 3x, now that you've seen that a couple times. And we're getting another 2/3. It looks like it's negative 2/3 this time. Negative 2/3. Hey, fraction ain't going away, right? Last one, another one with a fraction right here. If you work the power table out, you'll notice these are actually both powers of 3. 81 may be 9 squared, but 243 is not 9 to any power, not to an integer power at least. If this is 9 squared, a 1 over 81 would be 9 to the negative 2nd power, right? That's 1 over 9 squared. Let's rewrite that. And that's multiplied, that's raised to the negative 2n power, where the exponents will multiply. I'm sorry, I said we're not going to use 9. My bad. We're going to use 3. 3 to the 4th power is 81, so 3 to the negative 4th power there. 243 is 3 to the 5th power. So 3 to the 5th will be raised to the 2n minus 2 like that. I'm going to multiply these. I get 3 to the 8n here. And distribute this. I get 3 to the 10n minus 10 power. And I know that you feel like you're at the step possibly where you've matched the base early on. Don't get rid of them until you've actually truly matched the base. Just please, for my sake. You don't want to ignore some things that shouldn't have been. Anyway, set those equal to each other. And same thing, I don't add 10 to both sides. 10's in an exponent. You got to wait till this is grounded like that. Now I can add 10 over here, subtract 8n over there, and I'll get n equals 5. So there's that side, and if that's better for my students to have seen that work with harder problems before you get maybe an easier problem for a quiz, let's go with it. Those look good. 4 down, 6 to go. Skill number 20, distance and midpoint. The first 4 problems are graphs, and I'm going to work on them as if we only had the graph and we don't go off the ordered pairs. Okay? So I'm going to work kind of fast here. If you draw a right triangle here, you've killed 2 birds with 1 stone in helping yourself out, because the right triangle provides you Pythagorean theorem as far as a squared plus b squared equals c squared, if this were a, b, and c, like that. We're going to try to find the distance, c, how long this thing is by using a and b. How long is this? 4 units. Here, 2 units. I can set this up saying 4 squared plus 2 squared equals c squared right here. Try to find that c. C is kind of my distance. 16 plus 4 equals c squared. C squared equals 20. Now, I got to find c. I'm going to take the square root of both sides here. Now, for my students alone, I'm letting them know that you can keep it as square root of 20. You're good because it's exact. However, if you did round it, and I'm not checking right now, but if you did round it, I believe you get around 4.5-ish. It's not exact because it's irrational. There are some groups who are already simplifying radicals. If you are, I'm not going to teach it right now, but if you are, you can also write it as 2 root 5. That's something your calculator could also pop up if you do it the right way, the right kind of calculator. Square root of 20 there. Now, I said you can kill 2 birds with 1 stone by doing this slope triangle thing. And the reason is because the slope aspect. I'm running 4 and rising 2. The midpoint will be half that distance. I can go half of 4, which is 2, and half of 2, which is 1, and bam, land on that middle value right there, which is my midpoint at 2, -2. And that's all I'm going to leave it at right now when it comes to me talking about that right there. The midpoint is 2, -2 by doing half the distance on that set. When we hit numerical values, I'll give you formulas and work that out. All right, number 2, let's do the same thing. I'll just draw a triangle right here. Doesn't matter how it looks as long as it's a right triangle. Rise of 3 and a run of 4. And it doesn't matter where the directions go because I'll just make sure to do half of that when I find my midpoint. In fact, let's find the midpoint first this time. Half of 3 is 1.5. Go 1.5 up. Half of 4 is 2. You can kind of tell where I'm landing there each time to get these. That midpoint is at 0, -2.5. And I'm fine writing the decimal because we're all either going to get an integer or a 0.5 decimal if our coordinate pairs are all integers. So that one's good. When it comes to Pythagorean theorem, I have 3 squared plus 4 squared equals c squared, the unknown. Now, if you know any Pythagorean triples, you're going to know this answer is 5. But let's take a look. C squared is 25, and we're going to take the square root of both sides. 25 is indeed, though, a perfect square of 5. 5 squared is 25. C is 5. That is the length. Rational and good to go. All right, that's midpoint and distance. Let's keep moving forward. Number 3. And I'm just going to keep speeding up as I talk. Talk, 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 talk. Get the slope, slope triangle, sure, here, that right angle. This is a count of from 3 to negative, that's 8. And this is a count of 1, 2, 3, 4. Pythagorean theorem for distance first. 8 squared plus 4 squared equals c squared. After the side, I'm going to get water. I'm going to pause it. 8 squared is 64. 4 squared is 16. And c squared is 80. Take the square root of both sides. C will be the square root of 80. That is my final exact answer. If you know how to simplify radicals, that is 4 root 5, if that's what you're going for. Now, this number's about 9 because 81 is 9 squared. But I'm not going to just round it to 9. If it said 81, square root of 81, I would say c equals 9. It is not. This number's around 8.9 something. Very close to 9. Not exact. I'm not rounding. That's exact right there. I'm good. Number 4. Oh, excuse me, not number 4. Let's find the midpoint. The midpoint looks like it's right there, right? Half of 8 is 4. Let's do it the other way. Half of 4 is 2. Half of 8 is 4. I'm doing half of those. I'm landing at a midpoint of 0, -1. All right. Last one here of the graphed ones, number 4 here. Run and rise of, let's count it, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 5 squared plus 6 squared is c squared right there. That's 25 plus 36. which is 61. Not the answer. It's going to be the square root of 61. 61 is not only not a perfect square. I don't even think it's a composite number. I think it's a prime. No factors. So we'll leave it like that. The midpoint, if I were to eyeball it, I'd say it's probably that guy right there. Half of 5 is 2.5. Half of 6 is 3. And you're up right there at 2.5 comma negative 1, like that for the Z midpoint. Okay, let me pause for a second. Let me get my water right now. I'll be back. Okay, and I'm back. Not sure if I'm going to be able to average a minute or problem. I'm at 45 minutes right now. I'm not going to. And I'm not even halfway through everything here. But I can see where there's some purchase in. If you know algebra, I can go kind of faster on some other problems when I talk about them. All right, these next four are numbers. Now, there are still fast ways to go about this here. Let me write out the formulas that you have. Distance formula is this guy right here, which is a way of saying subtract your x's with each other, square it, subtract your y's. This is Pythagorean theorem, just a rewrite of it. So if I were to do distance formula with this, if I call this x1, y1, x2, y2, and I won't label these in the future, I'll say the distance here is the square root of x2, 4, minus x1, 2, squared, plus y2, 4, minus y1, 8, squared. 4 minus 2 is 2. We're going to square that. 4 minus 8 is negative 4. We're going to square that. 2 squared is 4. Negative 4 squared is still a positive 16. And I'm going to get the square root of 20. That is my distance. Not the midpoint, but the distance. Now, what did I do? I found the distances between, because, you know, what were we doing on graphs? Why was I counting these? I was doing the distance between my x's, because I can count that. From this x to this x, meaning negative 2 to 2, the distance was 4. From this y to this y, from negative 5 to 3, the distance was 8. Right? That's what I'm doing when we're subtracting that. And that's what's happening here. And I'm probably going to start doing that in some of these future problems. So when you see right here from 2 to 4, I ask, what's the distance from 2 to 4? You say 2. From 8 to 4, you say 4. Even if you said negative, we're going to square it. That part's not really going to matter there. So the distance is 2 and 4 in between there. And we work that out. We get square root of 20. Oh, or 2 root 5 if you work that out like that. Excuse me. The midpoint. First of all, midpoint formula. You average. The midpoint between two numbers is the average of those two numbers. You average your x values, add them and divide by 2. You average your y values, add them and divide by 2. You're going to get two different numbers from this, right? It's an ordered pair. It's an actual location. It's a point. So my midpoint for this one here, if I average my x's, 2 and 4, average my y's, 8 and 4, I'm going to get, and I'm going to cut over here for a sec, 6 divided by 2, which is 3, 12 divided by 2, which is 6. But, you know, midpoint is the middle value. If I asked you, what's the middle value between 2 and 4? You could all say 3. Between 8 and 4, you could all say 6. The numbers aren't always that easy. But I'm just saying that there are ways that, you know, if you mess up and put a minus here, 2 minus 4 over 2, you'll get negative 1. What's the middle value between 2 and 4? Is it negative 1? So what I'm saying is more of a double check. Can you double check that and say, okay, it's at least between the values. Is it right in the middle? Let's hope it is. All right, number 6. I'm going to do this right here. The distance between negative 6 and negative 2 is 4. Whether you say 4 or negative 4 doesn't matter because you're going to be squaring it. The distance between negative 8 and negative 8 is 0. Don't make a mistake and say 16. You're at the same value. So, what's the actual distance? I do have to use Pythagorean theorem. These 2 points right here are horizontally. Here's negative 6, negative 8, negative 2, negative 8. And you count 4 across. That is my distance. But let's go ahead and figure that out. 4 squared plus 0 squared equals c squared. You're overworking yourself. 16 plus 0, c squared. C squared is 16. Take the square root of both sides. You get 4. That's my distance. And c, by the way, you probably said, Mr. Robinson, you said c before and then you said d. Now you're going back to c. Which one is it? You can use x. You can use whatever you'd like. I use c when I write out Pythagorean theorem. I use d when I write out distance formula. And I tell you what, I don't write out distance formula a lot. You don't need it. It's a rewrite of Pythagorean theorem. You're going to screw up more stuff there than you're not, including messing up the formula itself, not squaring a negative and turning it positive, ignoring the square root at some point, being tedious with it, all that stuff. Midpoint. What's the number between negative? What's halfway between negative 6 and negative 2? What's that midpoint value? Negative 4. What's halfway between negative 8 and negative 8? Well, if it's the same value, the answer is negative 8. So I'm going to give you the answer first. Now let's average those numbers. Negative 6 plus negative 2 and negative 8 plus negative 8 over 2. Negative 6 plus negative 2 is negative 8. Negative 8 divided by 2 is negative 4. Negative 8 plus negative 8 is negative 16. Negative 16 divided by 2 is negative 8. And there you go. So I'm going to speed up through these next two here just to give you the answers and my approach with it. Oh, unless it's a little bit harder here. The distance between negative 6 and 1, it's not 5 though, it's 7. If you can tell, one of them's negative, one of them's positive, right? So if you did like negative 6 minus 1, you know, that's negative 7 that you're squaring. So the distance is 7 right there. So that guy's 7. From negative 5 to negative 4, that distance is 1, or negative 1, whatever. But we're going to do 7 squared plus 1 squared. That's 49 plus 1, which is 50. So C is the square root of 50. Now, as an exact simplified radical answer, that would be 5 root 2 for that crowd. But we can write square root of 50. A little more than 7, right? Clearly, 7 squared plus 1 squared. Oh, I just inhaled water. I might cough. I might choke. Midpoint. These midpoints are kind of weird. I'm going to go and do the average because you have an even number with an odd number. And they won't land on an integer. They will land on a decimal, some 0.5. So it might take you a little bit. Negative 6 plus 1 over 2. Add my x's. Average my x's, excuse me. Let's do that again. Negative 6 plus 1 over 2. And average the y is negative 5 plus negative 4 over 2. Which is going to get me negative 5 over 2. Which is a valid answer, by the way. You can leave it like that. And then negative 9 over 2. And again, you can leave it like that. That's acceptable. But if you'd like to write the decimal equivalent, that's negative 2.5 and negative 4.5. Then that way you can know where it's plotted on the graph. But the other one's good. Totally good. All right, number 8. The distance between negative 2 and negative 8 is 6. The distance between 3 and 8 is 5. So 6 squared plus 5 squared equals c squared. Really, I want to take that short route if I can. Even if I have distance formula, you can try distance formula and see you get the same thing. Just make sure that you do. So 36 plus 25, which is 61. We're going to take the square root of that. Was there a 61 before? I think there was. But it's a different set of points, right? And also a different midpoint. So the midpoint right here, we're going to find half the distance between negative 2 and negative 8. That's negative 5, right? There are 3. If they're 6 away from each other, half that distance is 3. 3 away from these guys is negative 5. Check that out. Let's average 8 and 3. 8 plus 3 over 2 is 11 over 2, which is 5.5. So negative 5 comma 5.5 is that. So hopefully logic is kicking in, even if I'm going faster or differently from how you would. See that you can get those answers and at least hear my logic if I use something slightly different there. All right, I'm going to move forward here because I'm halfway through the problems and not really halfway through time the way I'd like to be. All right, this is what's known as the segment addition postulate, which means when you have collinear points, such as these 3 right here, call them A, B, and C. And this is where a lot of geometry really starts. You're going to see a lot of different notations and things. I can add the length of AB with the length of segment BC and get the length of segment AC. Not going to talk much about the segment things, but when you see these two capital letters together, we're talking about the length of a segment from endpoint A to endpoint B like that. So these lengths add together to become the whole thing like that. Okay, so let's go ahead and start with some problems here, and they're really going to all run pretty much the same. 2x plus 25 is that length, 11 is that length, the entire thing is 27 plus x. So I can write an equation that says 2x plus 25 plus 11 equals 27 plus x. By the way, the instruction asks you to solve for x for every problem, and then find the length indicated. This does not ask you for a length, whereas this one asks for JL, if that makes sense. Combine like terms. This is the part where I'm going to whip fast. We did the algebra last. Skill number 2 was solving these kind of multi-step equations. Subtract x, subtract 36, and I get negative 9. Now, I will move forward, but you kind of, not that you want to double check your answer always. Maybe you do. I can double check. What's iffy is when you get a negative value because you want to think, you know, your lengths can't be negative. But the question is, does substituting negative 9 into here make your length negative? And it doesn't. 2 times negative 9 is negative 18, plus 25 is 7. 7 plus 11 is 18, by the way. Let's see if that works. 27 plus negative 9 is also 18. Yeah, they're the same length. Clearly negative 9 is the value, and it didn't make anything negative. So it works out. So negative answers can be had, just not negative lengths. Okay, we're going to find JL, the length from here to here, by plugging x into there, plus 4, or plugging x into there. But I got to find x. So x plus 5 plus 4, that plus that, boom, boom, equals 3x minus 3. Combine like terms. Subtract x over, add 3 over, divide by 2. I get 6. Not done. I need to find the length of JL. I can either, again, plug 6 into here. 6 plus 5 is 11, plus 4 is 15. Or 3 times 6. I'm going to do the one that's actually JL. 3 times 6 is 18, minus 3 is 15. And that is the answer that we're trying to find. Solve for x first, then find the length of JL. Okay, the next two are not drawn, but it's still the same idea. So make the drawing to get the labeling proper. So I actually have a tool where I can do this right here. Boom, check that out. I'm going to make point A, B, and C are collinear. B is between A and C. And they don't say it's right in between necessarily. It's not a midpoint. We're going to get to midpoints next, though. So I'll shift it off to the side, even if it's not drawn to scale. They say the length of BC is 2x plus 25. And the reason I'm drawing this is to make sure that I know exactly where everything goes. AC is 14. That's the entire thing. See how it's out of order? And AB is x plus 19. See, some people will just say this plus this equals this. And that's not what happened here. Not even close. It's this plus this equals this. So x plus 19 plus 2x plus 25 equals 14. I'm smelling a negative answer. Subtract, oh, that should say 14. Subtract 44 over, and I'm getting negative 30. Divide by 3, I get negative 10. That is x, and that's all they asked for. They said find x, and I did. And I said, here it is. All right, number 12. That was whipped fast. A, B, C. The length of AB is x plus 13. BC is 2x plus 25, again. And AC is 11. Kind of, it seems like a very close problem to what the last one was. Not really much difference here, guys. The difference is we are going to find the length of AB this time. So when you find x, you plug it in. So make sure you notice what the instruction asks you to do. So x plus 13, sorry about that. I didn't even realize these problems were pretty much nearly the same setup here. Why did I write 25x? That's a 2x. I was going to say, there's no way I'm adding that whole thing. That's why you don't talk while working on these. 3x plus 38 equals 11. Subtract 38, and I get negative 27. Divide by that, I get 3, I get x equals negative 9. Now we're going to find AB. Make sure that that negative doesn't affect this length being positive, and it doesn't. The length of AB is negative 9 plus 13, which is 4. And I'm sure that aligns with the answer there. I just did it mentally. It does. That's good. All right, the next 4. M is the midpoint of each segment. Now, this one's drawn for you, and they even graciously show you the tick marks. A midpoint, you kind of know what it means on a graph, and it means the same thing here. It's half the distance between these two guys right here, which means these two segments are now congruent to each other. And that's how we're going to write equations this time. Sometimes. We're not always going to say this plus this equals some whole thing. No, instead, actually, x plus 6 equals 3x. That's what the midpoint allows you to do. I couldn't have done that here. I didn't know this was a midpoint or not, and it actually wasn't, but I'm not going to make an assumption. Here they say it's the midpoint. These are congruent by the tick marks. We go. We get x equals 3. I'm actually done with that problem. Next one, same thing, draw M's the midpoint of these. I'm going to set them equal to each other, and then find the length of JM, which, by the way, will be the same thing as length of MK, because they are congruent. That's why I make this equation to begin with. Set those equal to each other. Subtract 6x and add 13 and divide by 3. I get x equals 8. JM, that length, I'm going to take 6 times that 8 that I found plus 11. 48 plus 11 is 59, and that is my answer. Yes, I know I'm going fast. I'm being time conscious. To slow down, I'll say if I substituted 8 into here, 9 times 8 is 72. Minus 13 is also 59. So even though you're not supposed to be doing both necessarily to find that answer, you can double check and make sure it worked. They were supposed to be the same. Okay, this one does have midpoints featured based off this. A, B, and C are collinear. Now this time B is the midpoint. So this time you might want to draw in the middle, but furthermore, you need to mark these congruent so you know what you're going to do with this. This problem's a little different right here. This time it says AB is 2x minus 10, great, but they don't give us BC. They say that AC is 3x minus 11. Now, don't make the mistake of what we just did last time, which wasn't a mistake before. Don't set these equal like this. 2x minus 10 doesn't equal 3x minus 11. 2x minus 10 is half of 3x minus 11. You want to get you want to get these equal to each other, you got to double 2x minus 10 right here and right here. So what I could do is I could literally double it like that. That's one approach. Alternatively, which is the same thing, alternatively, if one is 2x minus 10, I can express the other as 2x minus 10. And 2x minus 10 plus 2x minus 10 will give me the same thing as this will right here when I double this by distributing, and I get 4x minus 20. So for the most part, you'll probably see me say the doubling thing, but I might add them up like that. I don't know, but I'm going to solve. Subtract 3x, add 20, and I get x equals 9. And all they asked for was x. This time they're going to ask for the length of AC. Are there questions on that one? Ask in the comments down below. I'm not live streaming. All right. A, B, C, collinear. B is a midpoint. This one actually should be easier when it comes to the solving. 5x plus 15 for the length of AB. X plus 47 for the length of AC. These actually equal each other this time. See the difference between those? And I subtract x over, subtract 15 over, divide by 4, I get x equals 8. Substitute 8 in for, now they want AC. AC is the entire thing. Where do I substitute it? I could substitute it into both. 5 times 8 plus 15 and 8 plus 47. And add those both together. Now 8 plus 47 is 55. This should also be 55. They were the same after all, but I do have to add them both. 5 times 8 is 40, plus 15 is indeed 55. 55 plus 55 is 110. That is the length of AC. Sorry for writing it up there. Let me kind of brighten it up so you know exactly what I was pointing at. Oh, that's bright right there. Okay, and that's my final length for that. All right, there's that skill. The next skill is using angles in the same fashion. Skill number 22, if you will. This is called the angle addition postulate instead of the segment addition postulate, where the measure of one angle plus the measure of the other angle equals the measure of the whole thing when they are adjacent to each other. And that's exactly what this is. Now, you can see this stuff right here, and I got to clarify what it says. This says the measure of angle IJK, and this is a bad example to talk about an angle here because it looks like a straight angle. Let's look at one that's more obvious, like this GHI, measure of angle GHI. That means they're talking about this angle right here, GHI, like that, and that's 158 degrees, if that makes sense. This one's a straight angle. When they say IJK, I don't know if it's actually a straight angle, but it looks very straight. There's no bend, so you're like, what angle, right? There's that vertex of J, though. Anyway, the entire expression for IJK, this is not a length. This is an angle measure, 21x plus 12 degrees. The sum of 14x minus 2 with 70 degrees gets us 21x plus 12 degrees. Add this with that to get whole thing. So we're going to solve algebraically, right? We set up geometrically. You set up an algebraic equation, but you use geometry and the concept of the angle addition postulate and measures and such to make that happen. Anyway, I'm going to get x equals 8 right here. I subtracted 14x over and subtracted 12 over right there, and they divided both sides by 7. They said find x. I did. All right, this time we're going to find the measure of an angle after they give us this information here with these labels. Measure of angle CDE, the entire thing, is 164 degrees. That is this inside concave part right here. We're going to add 12x plus 8, this guy, with 3x minus 9, that guy, and get 164. Use algebra to solve the rest of the way here. I'm sorry, that's still 164. I'm thinking one step ahead when I'm going to add 1 over. 164. 65, and I think that's 11. So x is 11. Now I got to find the measure of angle WDE. That is this guy right here. It is expressed as 12x plus 8. I found that x was 11. So I'm going to do measure of angle WDE, and that's 12 times 11 plus 8, which is 140, and that is in degrees right there. The other ones didn't have units for length. If they said inches, I would have put inches, or I could have written units. Angles have a degree measure. We are going to put it every time for the measure of an angle. X, technically not an angle in and of itself. It's a variable within an angle's expression, so I don't need degrees for that. The measure of an angle, I do. All right, number 3, and 4, it's just like the last ones. Just make sure you know what you're solving for, but nothing's labeled. The drawing is there because you want to know what's in between what. The drawing's there, it's just not labeled. GHK, this guy here, is x plus 140, so I'm going to do the labeling myself. GHI, the whole thing, is 158 degrees. And this little guy, KHI, is x plus 30. So it looks like we're going to add x plus 140 with x plus 30 to get 158. Once again, it's really good to label it so you know which ones add to become the big guy. 2x plus 170 is 158. 2x is going to equal, looks like negative 22, so x is negative 11. I guess that's right. Negative 11 plus 40 is 129. Negative 11 plus 30 is 19. 19 plus 129 is 148. 158. Oh, did I do that right then? $129 plus 19. No, that's 148. What did I do wrong? Oh, that's not negative 22. Let's do that again. See, we double check. That's what something fell off. That's 12. 2x is negative 12. X is negative 6. Okay, I'm going to trust that and move forward. All right. Next one, we're going to find the measure of angle WFG, which is 55x, but I got to solve for x first. WFG is 55x. EFG is 72x plus 2. That's the big guy. EFG. We're hitting the whole alphabet. And EFW is 36 degrees. That's the little guy there. So 55x plus 36 equals 72x plus 2. These terms do not combine right there. We will combine the 55x with 72 when we subtract it over and get 17. Subtract that over, we get 34. Divided by 17, we get x equals 2. The measure of angle WFG, now these are kind of drawn to scale. Like, I didn't draw them, but I imagine it's going to be this number, 55 times 2, which is 110 degrees right there. That looks like a 110 degree angle there. Looks like they knew what was up. All right, in each figure, the segment bisects the larger angle. So this WP right here, sometimes it's a segment, sometimes it's a ray, it goes right in the middle of these two. So angle 1 and angle 2 are congruent to each other, not in terms of length, but angle measure. That's not 1 degree and 2 degrees. For one, those aren't the same. That's just the label of them. We're going to find x if the measure of angle 1 is 18x minus 2, not labeled. Measure of angle UWV, that's the whole thing, is 34x. This is just like the midpoint. This is a midterm review. The midpoint thing for segments, where I have one part and the whole thing. I could double this to equal the whole thing, or I can express angle 2 as 18x minus 2 as well, because they're the same thing. So if I do 18x minus 2 plus 18x minus 2, then they add together to make the whole thing. So it looks like you were missing a piece, but because they're congruent, that's going to happen. 36x minus 4 is 34x. I'm going to subtract 34x to get 2x, add 4 over, and divide by 2. I get x equals 2. They just wanted x, and I'm good to go. Find x once again. Measure of angle 2 is 3x plus 14. Measure of angle 1 is 4x plus 6. I'd argue this problem's easier. These are just set equal to each other. This is a bisector after all. So 4x plus 6 equals 3x plus 14. Very much easier. I subtract 3x. I subtract 6. I get x equals 8. I'm done. I'm moving forward. Number 7. We got to find the measure of angle 2 now. So we solve for x first. Measure of angle 2 is 4x plus 9. Hey, I found it. No, we got to solve for x. And TRS, the whole thing, is 12x minus 6. If one is 4x plus 9, so is the other, or we can double the angle measure. Let me say it that way. Let's double the angle measure. That way you kind of know that you can do one or the other. It's 12x minus 6. Here we get 8x plus 18 when you distribute that 2 into there. I'm going to subtract 8x over to get 4x, add 6 over to get 24, divide by 4, and you get x equals 6. I need the measure of angle 2, which will be the same as measure of angle 1. I'm just whatever there. But the measure of angle 2 is going to be 4 times 6 plus 9. That is, I just wrote a 2. 4 times 6 plus 9, which is 24 plus 9, which is 33 degrees. That's the measure of angle 2 right there. Measure of angle 1 should be the same, clearly, and this should be double that. It's 12 times 6 is 72, minus 6 is 66. But I just want a measure of angle 2. Now we want the measure of angle BDC. We want the whole thing knowing angle 1's measure and angle 2's measure. That is angle 1, sorry. Angle 1 is 4x plus 3. Angle 2 is 5x minus 2. Keep in mind, though, they're expressed differently. They are the same measure, though. That's the whole point of the bisector. So we're going to set these equal. 4x plus 3 equals 5x minus 2. Subtract 4x. Add 2, you get x equals 5. They want the measure of angle BDC. Now, it is the sum of both of these things together. I can substitute 5 into x for one of these, like this right here. Measure of angle BDC, whole thing. I'm going to take 4 times 5 plus 3, just the measure of angle 1, and I'm going to double it. I'm going to double whatever I get. 2 times 20 plus 3, that's 46 degrees right there. Again, I would get 23 with this one as well. 5 times, what was it? 5? 5 is 25, minus 2 is 23. 23 plus 23, 23 times 2, 46 degrees. Okay, I have 2 more skills, I believe. Well, 3 more. But the last 2 are kind of one the same. I'll see what I can do with those. Those first sets, we've done slope. I don't know if I've done it with you guys, but I'm just going to write out the formula and work it from there. Slope is the change in y over change in x. And it's probably worth it to use it for the most part on these unless you know which direction you're going correctly here. So I'm going to write this often. I think at some point I'll shut it down, maybe on the last 2 problems here. We want to find the slope of segment AB right here. Slope of segment AB. And that's going to be, y2 minus y1 over x2 minus x1, like that, subtracting the negative, all that jazz. That's negative 28 over positive, 4 minus negative 3 is 4 plus 3. Positive 7, which is negative 4. I'll tell you what I'm going to do with these after. I just wanted to jump into the problem because I was so excited. The next part, the slope of CD right here, segment CD, and that's what we're going to do for each of these. We're going to find their slopes and determine whether these slopes are parallel to each other, whether they are perpendicular to each other, or whether they're just neither. They do something else. They just intersect in some other kind of way. Now, parallel lines never intersect. They run this direction. Perpendicular lines run at 90-degree angles with each other. And there's something about the slopes that we're going to look at to see the truth on that. So both these have a slope of negative 4. The slopes are the same. If they are the same, the lines are parallel. So I'm going to say these ones out loud. Parallel lines have the same slope, identical. And you want to reduce your fraction to make sure that they're actually the same. Perpendicular lines have what's called an opposite reciprocal slope, where you're going to see a flipped version of the fraction, or whatever it is, or some form of that, and the sign is going to be changed. The sign's going to be the flipped version. So let's try that again. Let's do slope of this guy right here. 2 minus 8 over 3 minus negative 3. That's going to be negative 6 over positive 6, which is negative 1. You can put negative 1 over 1 if you want to. This guy right here has a slope of negative 1 minus 1 over 5 minus 7, which is negative 2 over negative 2, which is positive 1. Now I have a negative 1 and a positive 1 right here. Now if you keep in mind, 1 is 1 over 1, or negative 1 is, so this one's also negative 1 over positive 1. This is positive 1 over positive 1. You can argue the sign changed. Well, it did. The sign changed, but you could also argue that the fraction flipped. The 1 over 1's flipped over, right? You swap from one to the other. Kind of a weird way of looking at it, and I don't know if you're going to get a natural opposite reciprocal slope here, so let me talk about a natural one. What if you have 5 halves and negative 2 fifths? Those are opposite reciprocals of each other. Those will intersect perpendicularly. So will these. I just want to make sure that you see what it means when I actually truly mean opposite reciprocal. These are opposite reciprocals. These are perpendicular. All right, next set right here, number 11. This is where, let's see if we can do this kind of in our head. I don't know. I don't know if you're going to be able to do it in your head. I'm not going to. I can, negative 2, all that. So slope is negative 10 minus negative 8 over negative 2 minus 5. The problem between this and my whole distance formula stuff that I did was the signs matter here. So I could ask you what's the distance between negative 10 and negative 8. You could say 2. That's great. But the signs matter in what you have. Here I have a negative 2 over negative 7, which, by the way, is positive 2/7. So there's a slope. The next slope here, this guy, is 1 minus negative 13 over negative 2 minus negative 6, which is 14, positive 14 over negative 4, which is negative 7 halves. Oh, there's an opposite reciprocal slope. Okay. So it reduced. So you see that reduction right there? 2/7 and negative 7 halves. That is a perpendicular slope right there. I was ready to say neither for that for a moment. Oh, hold on. No. I screwed up. I did screw up. Not everything, just this sign. You see? I messed that up. That's not a negative 4. That is a positive 4. So that's 7 halves right there. 2/7, 7 halves. They are reciprocals. They are not opposite reciprocals. This is, yeah, I was thinking, kind of looks like a neither when I was doing something there. This is a neither case right there. It looks like it wants to be, but the signs aren't different. Therefore, it's a neither case. But do reduce your fraction, right? Every time you work with slope, that's something you're going to want to do. All right, this one's going to be a little bit different right here. What happens is, here you got a slope of, let's calculate them first. 7 minus negative 2, let's say that aloud. 7 minus negative 2 is 9. 0 minus 0 is 0. 9 divided by 0 is undefined. Undefined slope. That doesn't mean there's no line that works it. That's a vertical line right there. Boom, boom, like that. This guy right here, on the other hand, has a slope of negative 5 minus negative 5 is 0 over 6 minus 3 is 3, and 0 divided by 3 is 0. That's a horizontal line. A slope of 0 to slope of undefined are indeed, I don't know if I want to call them opposite reciprocals of each other, but you see how that flips 0. Doesn't matter what's the other number. That could be 0 over 9, 9 over 0, 0 over 3, whatever it is. 1, 0, 1's undefined. These are perpendicular. It's kind of a tricky set, but the fact is they are horizontal and vertical lines. And like an x and y axis, those are perpendicular to each other. I mean, that's it and that's all. Actually, need I say more? No. All right, 13 through 16. We're going to write the slope-intercept form of the equation of the line described. Slope-intercept form is y equals mx plus b, and I can even see y equals mx plus b right here. We're going to write the equation of a line that is parallel to this one. You can see parallel, parallel, and then here you can see perpendicular, perpendicular. So, or you can't see that one right there. But parallel will mean same slope. So I want to make an equation that has the same slope as this. I'm going to use the slope of 6. I have an equation that says y equals 6x plus b. I need to find the proper b that passes through the point -1, -4, -1 for x, -4 for y. This stuff is not new to last semester material with the exception of the parallel or perpendicular, and that is the only part that's new. So I'm going to go fast on this here. -1 can substitute for x, like that, and -4 can substitute for y, like that. And then I'm going to get a b value. That's -6, that's b. Add 6 over, I'm going to get a b value of 2. I got a slope of 6 and a y-intercept of 2. My equation will say y equals 6x plus 2. That was y equals 6x minus 2. This is y equals 6x plus 2. Those are parallel lines. All right, the next problem right here. This is not, my slope is not necessarily 2 here. I have to get this in slope-intercept form to get the actual slope. So I'm going to start by subtracting 2x over, and then I'm going to divide everything by 3. 3, 3, 3, and I'm going to get y equals -2/3 x minus 1. Now I'll be honest, this isn't my answer. This is this equation rewritten. Now I'll be honest, I couldn't care less what this y-intercept was right here. I'm going to get a brand new y-intercept with this point that I have. So I'm going to take this -3, -2, for a y equals mx, my slope is -2/3 that I'm going to use. The whole point of getting that equation there was to use this -2/3 slope. And I'm going to substitute -2 for y, -3 for x. -3 over 3 is -1, times -2 is +2. And if I subtract 2 over, I'm going to get b equals -4. So I now have an equation. Slope of negative 2/3, y-intercept of negative 4. Sorry, you can't see that. Will be y equals negative 2/3 x minus 4. Again, I couldn't care less what that y-intercept was. I needed this y-intercept by first getting this slope, by getting this in slope-intercept form from before. You can see how much I wanted to speed up. I'm kind of running on fumes. Number 15, perpendicular. Now this time, whatever this thing is, notice how the original slope is negative 1/2. I need the perpendicular slope, the opposite reciprocal. Change the sign to positive, flip this to a 2/1, or just 2. 2/1 is just 2, right? This is the slope I'm going to use. I have an equation that's going to say y equals 2x plus some b. I got to find that b, plug in this for x, this for y. Negative 1 equals 2 times 1 plus b. 2 times 1 is 2. Subtract 2 over, and I get b as negative 3. So I'm going to use that slope, that y-intercept, and write the equation y equals 2x minus 3. Hopefully that's kind of making sense what I got there. Opposite reciprocal slope. Same thing here. This is not yet, this is in standard form to start with. I got to subtract x over. Negative y is negative x minus 3. Divide everything by negative 1. I get y equals positive x plus 3. The slope of this guy here is 1. 1/1, if you will, because the opposite reciprocal slope is negative 1/1 or negative 1. So I'm going to be using a negative 1. Sorry if that's tricky for you guys. We just got a test of that on like number 2 or 9 or whatever it was up above. Number 10, I think. So my equation is going to be some sort of y equals negative 1x plus b. And I'm going to write a cleaned up version of this a little bit later here. I'm sorry. Yeah, perpendicular to. Yeah. That sounds right. Negative 5 is going in for x, 5 going in for y. So 5 equals negative 1 times negative 5 plus b. 5 equals 5 plus b there, and b is 0. Now, there's one way I could write this, which with the slope of negative 1 and a b of 0, it would be y equals negative 1x plus 0. Another version of that is just y equals negative x. Negative 1 times x is negative x. Anything plus 0 is just itself. So either or is an accepted kind of version of that value or variations of it. But if you see that, you got to know what it means. Just like with this x from before, right? This x meant the slope was 1. You have to know that. You have to. That's its implied value. Anytime I solve for b, that means 1b, right? That's something to know. All right, last set of problems right here in skills 24 and 25. They all mean well as far as the same thing. 24 are these angle relationships, so are 25. 24 is the start of knowing angle relationships without using variables. 25, we use the variables with the same angle relationships. I might even have a video with this information of these problems, this problem set, but we'll do it. Find the angle measure of b in the first two problems here. Now, I'm just going to introduce them as they are. B and 72 are known as vertical angles. These are two angles that are opposite each other when two lines intersect. Now, I say two lines intersect. There was another line right here. The point is the lines that make the angles you're talking about. These two in blue right here make these two angles. These are known as vertical angles. Those are angles opposite each other when two lines intersect, and vertical angles are always congruent. That's pretty easy then. If this is 72, then B is 72. I don't even have to do any math for that. I just solved it. Degrees, by the way. This next set here, this B and this 129, you see where the angles are formed by these two lines. B is made by these two. 129 is made by these two. So in total, if I really ignore that triangle look right here, I'm really just looking at that guy right there. Does that make sense? Hope so. I can hide it. See that? Now, B and 129 are known as what's called a linear pair. They form together to make a straight angle. They are adjacent to each other. They connect. And they are supplementary, which means they add to 180 degrees. B doesn't equal 129. B plus 129 equals 180. That's a 180 degree angle measure. I solve for B by subtracting 129, and I get 51 degrees on B, and that's it. So that's a linear pair. I'm going to try and identify these whenever I can. Once again, vertical angles, linear pair. And I'll be honest, this is skill 25 right here. I got vertical angles right here. They are congruent, vertical angles. I'm going to set them equal to each other. And I'm going to solve for x. Subtract 1. Divide by 4. I get x equals 21. I don't have to put degrees. It's within that actual whole measure in and of itself. And number 4, this is a linear pair right here, where these two add to 180 degrees. I can combine like terms and subtract 143 over, and I get 37. Again, not necessarily degrees there. Okay? Now, those were angle relationship names, vertical angles, linear pairs, when two lines intersect. What you're going to start now looking at, and I'm going to call them out first, and then I'm going to do the actual problems. I'm just going to use these lines here, though. These next sets are when things have two lines intersecting with a third line, also known as a transversal. And there are a lot of different kinds of problems I can do with these, complicated, much more complicated than what we're going to look at here. Through these, there are these angle types. This is called corresponding angles right here. Angles that flow in the same direction. Those are corresponding angles. These are corresponding angles. These are corresponding angles right here. On the same side of the transversal, flowing in that same direction. Those are clearly what you're looking at right now are not corresponding angles, but you see the name, corresponding angles. Then you have what are called alternate interior angles. If you notice here, here's that transversal I was talking about. This is opposite sides of the transversal and in the interior of there. What you're doing is you're relating angles up here with angles down here. And I just related this angle with that angle. These are known as alternate interior angles. So are these two, which by the way would be the answer of this, alternate interior angles. Also, I call it AIA, alternate interior angles like that. I'll circle that later. Let's look at alternate exterior angles, opposite sides of the transversal, outside of your two lines that are intersected by the transversal. Alternate exterior angles right there. And then this is known as same side interior angles right here. Same side of the transversal, same side interior angles in the interior. And then same side exterior angles right here and right here. Now, there are certain relationships that happen when these lines are parallel. They may look parallel right now, but we can't assume that they are. And furthermore, we're not doing anything mathematically with them right now anyway. But the lines don't need to be parallel for this name to be as such. These are alternate interior angles, whether or not the lines are parallel. Even if the lines look like that, these are still alternate interior angles. They're just not congruent anymore, like they would be. All right, these are corresponding angles right here, flowing in the same direction, same side of the transversal. We're just identifying them right now. We're just identifying. Those first two are multiple choice. These next two are free response. So I'm going to write those out. These are same side interior angles right there. They're not congruent when lines are parallel, by the way. And these are alternate exterior angles right here. So I'm trying to identify some of them for you, and I'm writing them out. All right, last page right here, and 6 more problems. Identify the angle relationship and find the angle measure. Find the measure of each angle indicated. The question mark's the one indicated. I'm going to put an X because I like to use algebra. Now, you notice these arrows here. Those mean the lines are parallel. That means that you're going to have relationships of either congruence or supplementarianism. They're either congruent or supplementary. Just like vertical angles are always congruent, linear pairs are always supplementary. When lines are parallel here, you're always going to get a set of congruent or supplementary. Alternate interior angles, which by the way is identifying the angle relationship, alternate interior angles are always congruent when lines are parallel. You can tell as well they're very obtuse with each other. No way they add to 180 if they're both way more than 90. Anyway, x equals 129 degrees. That is the answer. Looks like it's also a multiple choice option for me right there. Number 10 is a free response, and this x is this unknown right here. This is known as the same side interior angle pair. They are not congruent. You can tell one looks obtuse, one looks acute. There's no way they could be the same. The lines are parallel. Same side interior angles are supplementary. So if I'm going to solve for x right here, I add them up to 180, and I subtract 76 over, and I'm going to get x equals 104 degrees. Not, I forgot what I was going to say, but not congruent. They're supplementary. Identify the angle relationship and solve for x. I think it's the same thing. Oh, now it's a little more algebra. Corresponding angles right there. When lines are parallel, corresponding angles are congruent. So 70 equals 7x plus 7. I can subtract 7 and divide by 7. I get x equals 9. And that's my answer right there. Corresponding angles, corresponding angles are the forefront of all of this, right? They are the foundation of this. I just take this angle and I just move it down right there. I mean, they have to be the same. Do not say they're supplementary. I mean, come on. They're congruent. Now here I have a vertical angle pair. Vertical angles, remember, it doesn't matter if there's another line here. It doesn't matter if the lines are parallel. It has nothing to do with the fact that these two lines intersect and these angles are opposite each other. By the way, I didn't identify these. These are corresponding angles. And this here is a vertical angle pair, which are still congruent even if there's a line cut by a transversal. Don't say alternate exterior. That's not in the exterior. Vertical angle pair, they are congruent. Solve for x. Subtract 4. Divide by 7. I get x equals 8. Okay? Last two problems and then I am done. Here we go. Identify the angle relationship and find the measure of the angle indicated in bold. That's the one in bold there. That's the one in bold there. I hope you can kind of tell. I know when I print these out, my students can never tell. All right, these are alternate exterior angles here. This time they are. And as you can tell by the acute measure, all the alternates, vertical corresponding alternates are congruent. Linear pair, same sides, are supplementary. When lines are parallel for those things, and lines are clearly parallel. So set these equal. Subtract 4x over x is 11. I'm not done because I need to find the angle indicated in bold, 5x. 5 times 11 is 55 degrees. So we're going to get that answer, 55. This is also 55, by the way, but it's not the one indicated in bold. All right, and this last one here is a linear pair. Once again, they are adjacent. They form to make a straight angle right there, a linear pair, and linear pairs are supplementary. It had nothing to do with this line or it being parallel. They do not equal each other. They add to 180 degrees. They are supplementary. Last problem. So, you know, another reason I'm rushing is I think I'm running out of computer storage space. So I think I'm limited. I don't want this recording to stop on me when I'm doing the problem. So I'm going to have a pretty quick sign off at the end here. 27x equals 189. I don't know that number. 54, 81, 108. Shoot, I'm not counting. It's 27 times 4. I think it's 7. That's a lot faster. I don't know why I was doing it the way it was. It's 7. X equals 7. Not done. Let's substitute 7 into this one. Now it matters because this angle is different from that one, right? 16 times 7 minus 7 is going to be 95. I think 95 degrees. It's not multiple choice, so I'm not certain there. I'm going to try the other one. 11 times 7 is 77 minus 2 is 75. Oh, it's not. It's not. It's 105. 105 degrees. See, that's wrong. Good thing I double checked. I didn't want to be wrong in the last problem there. Okay, and that is it. Sorry if I'm clipping. I'm just yelling. That ought to do it for this one, guys. Hour and a half. Not too bad. A little longer than the last set. Mine's probably getting a little red there. This is Mr. Robinson. Thank you so much for watching. I hope all of this was helpful for you. Welcome back. I don't know if I'm recording any videos pretty soon here on out, but glad to be with you again. Take care, and I will see you in the next one.